When you interact with ChatGPT, the experience feels frictionless, a clean conversational exchange that mimics human thought. But beneath that interface lies a different reality. Billions of lines of raw, unformatted HTML, scraped from the messy corners of the internet to feed an algorithm. If you peel back the interface, the words disappear. What remains is a one-dimensional sequence of integer IDs, the only language the machine actually understands. There is no persistent self behind the screen. An LLM is a stateless algorithm. It does not have a continuous stream of consciousness. It boots up to process your specific sequence of tokens and shuts down the instant it produces an answer. Think of it as a token tumbler, a mechanical system that uses massive statistical tables to calculate which chunk of text is most likely to follow the one before it. This purely statistical nature creates a strange contradiction. These systems can pass the bar exam and write complex code, yet they often fail to count the number of R's in the word strawberry. To understand why a model can conquer legal theory but fail at basic counting, we have to trace the three-stage pipeline used to build it: pre-training, supervised fine-tuning, and reinforcement learning. When you stop viewing an LLM as a continuous mind and start seeing it as a mechanical pipeline, you can begin to predict its errors and manage its outputs. It starts with pre-training. This is the brute force ingestion of the web. Engineering teams filter roughly 44 terabytes of raw text down to the highest quality documents to create a training set. Turning that data into a model requires immense physical power. Thousands of specialized chips, like the NVIDIA H100 seen here, work in parallel for months to process the volume. Because neural networks process math rather than letters, the text must be translated into a set of discrete symbols that the computer can handle. This is done through byte pair encoding. It's an algorithm that compresses human language into a fixed vocabulary of about 100,000 unique chunks, called tokens. A complex word like ubiquitous is not seen as a string of letters. The model views it as three separate IDs: U, biquit, and OS. The model cannot see inside these terpins. To the network, they are indivisible units, the atoms of its universe. This is the root of the strawberry problem. If the letters are baked into a token, the model can't count them, any more than you can count the individual grains of flour in a finished loaf of bread. It only sees the integers. Once tokenized, the IDs enter in transformer architecture, a fixed mathematical grid where billions of parameters interact with the input sequence. Every pass through this equation ends with a probability distribution. The model isn't knowing the answer, it's just guessing which of those 100,000 tokens is most likely to come next. The result of this months-long process is a base model. At this stage, it cannot answer questions or follow instructions. It simply auto-completes text based on the statistical patterns of the internet. This model is a lossy simulation of human knowledge. It has absorbed the world's data, but it has not yet been taught how to be an assistant. To turn a simulator into an assistant, we move to supervised fine-tuning. Instead of the whole internet, the model is trained on a curated dataset of multi-turn conversations written by human experts. Engineers inject special structural tokens, invisible markers that explicitly label which parts of the text are from the user and which are from the assistant. These tags act as a strict protocol, formatting raw text into the back-and-forth structure we recognize as a chat. Through this training, the model learns to adopt the persona of a helpful assistant, statistically imitating the tone and format of the human labelers. When you ask for the top landmarks in Paris, the model provides a polished list, because it is simulating the research a human labeler would have done when creating the training data. However, SFT creates a psychological trap. Because the training data consists of experts giving confident answers, the model learns that the correct statistical move is to always sound certain, even when it doesn't know the answer. This forced confidence leads to hallucinations. When a model's blurry internal memory fails, its training compels it to invent a plausible-sounding fact rather than admit ignorance. To fix this, developers interrogate the model with verifiable data, like the career stats of an NHL goalie. By finding exactly where the memory breaks, engineers add examples to the training set where the only correct response is to refuse to answer. This highlights the two types of memory in an LLM. There are the billions of parameters, its baked-in, blurry long-term memory, and the context window, which is its precise temporary working memory. We can bridge the gap between blurry parameters and verifiable facts by giving the model access to tools. When a model emits a search token, it pauses text generation. A search engine retrieves the necessary data and slots it directly into the context window. Now the model doesn't have to guess. It can read the facts directly from its working memory, overriding its lossy parameters with the text right in front of it. The final stage is reinforcement learning, or RL. If pre-training is the textbook and SFT is the worked solution, RL is the practice exam where the model is rewarded for finding the right answer on its own. This stage addresses a physical bottleneck. Every single token the model outputs is the result of a fixed, finite amount of mathematical computation. You can see the failure of this limit in multi-step problems, like a word puzzle involving Emily's apples and oranges. If you demand the final answer immediately, you are asking the model to cram every variable, every subtraction, and every division into a single pass of the network. There is only a fixed number of layers in that pass. If the logic requires more steps than the network has layers, the model is physically incapable of reaching the correct result in one go. The solution is to let the model generate intermediate tokens. By solving one small piece of the equation at a time, the model spreads the work across multiple passes. Each intermediate output becomes the working memory for the next pass. This turns the sequence into a cognitive scratchpad, distributing the computational load. When the problem is broken down, the model can safely arrive at a result that would have been impossible to calculate in a single leap. Reinforcement learning explicitly rewards the model for using this step-by-step strategy, teaching it to show its work, rather than rushing into a high-speed hallucination. Every token generated is a discrete cycle of processing. Forcing an immediate response restricts the model to a single pass of logic, while intermediate steps allow the system to build on its own outputs to reach more complex conclusions. Pulling back from the math, we can see the full mechanical pipeline. We see the conversational persona carved out by fine-tuning. We see the massive, blurry statistical memory formed during pre-training. And we land back at the chat box, but the mystery of what's behind it has been replaced by a clear blueprint. Pre-training provides the knowledge base. SFT provides the assistance voice, and reinforcement learning provides the computational space to process logic. In practice, this means you should always use external tools to anchor the model's blurry memory, and always mandate a step-by-step process to give the network the computational runway it needs. These models are not impenetrable mysteries. By accounting for the stages of this pipeline and the constraints of the architecture, you can move past unpredictable text generation and begin to use these systems as tools for reliable, verifiable results.